right? Okay, fine. So let us start, and we were discussing about the AC sources, right? So in this actually alternating current, so most popularly it is AC, right? And here we were talking about, so we already understood what is DC, and even the research also actually first the DC was invented, and actually we were used to DC, and almost hundreds of years actually we were running with DC, and then actually later actually the AC actually got the traction after the invention of the induction motor. Now obviously when we know something, when we wanted to learn something new, then everything we will try to compare with our old version, right? Then actually it is easy for us to understand. So in that context actually there is something called average value and RMS value comes into picture, right? So let us understand what is this average value and the RMS value. Now the average value, so this was asked once in UPSC, right? Average value. Now let me explain what is this average value. Suppose I have actually 10 data points. Let us say 1, 2, 10, 5, 3, 7, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 8 values. And actually 9, 7, 3. So 10 values are there. Now if I ask you to calculate what is the average of these values, then how do you calculate? You will add up everything. 1 plus 2 plus 10 plus 5 plus 3 plus 7 plus 5 plus 6 plus 9 plus 7 plus 3 divided by 10. So this is the way actually we calculate the average value, right? So this is the way we calculate the average value. Now coming to the AC, suppose actually if I ask you to calculate, let us say, so I have given actually there is a triangular waveform like this, and then actually there is a triangular waveform like this, and there is a triangular waveform like this. So this actually continues until infinite. Now let us say, so this is the time period capital T. Now if I ask you to calculate the average of this particular waveform, so average value of this particular waveform, how do you calculate? So here actually the value is 0, and let us say this is the highest value, let us say V, and then actually at every minor point actually you will have some or the other value. So some or the other value actually you will take it, right? Now if I ask you to calculate, what is the possible methodology we can use to calculate the average of all the values that are present on this particular line? And how many values that are there? Yes, how many values it can be? So there are infinite possible values are there. Now how do you calculate the average of that infinite possible values? So we can use the integration, right? So integration actually what it will give? By definition, the integration under any curve, it will give the area, right? Correct or not? It will give the area. That means suppose actually if I have this particular curve, so y is equal to simply t. So or v equal to t is the curve, so which represents this particular straight line, and then actually this is in between 0 to t. Now if I calculate integral t dt, t dt meaning, so or actually integral v dt we will calculate. So integral v into dt. So whatever may be the curve of v, suppose actually if it is a sinusoidal waveform, then actually the sinusoidal waveform curve, this is v of t, and this is v equal to t, which is the v of t value. And if you take any other waveform, depending upon the function, so v may be any random function of t, right? So this is how actually the voltage waveform is getting represented. And that voltage waveform, if you calculate v into dt, v may be a function of t. So v may be a function of t. It can be any function. It may be a sinusoidal waveform or cos waveform or a triangular waveform or a stepped waveform or a unit step function. It doesn't matter, whatever maybe it is. But essentially this value, it will give the area under this curve. But I wanted to calculate the average of all the values of v. Then how do you calculate? It will give the area, right? Correct or not? I hope you understood my question. See, I have calculated the area under this curve, but I wanted to calculate the average of these values. How do you calculate the average? I am not talking about the area. Yes, how we can calculate? Right? It is very simple. If you notice v into dt, which is the product of the function, the height, suppose actually if you take a random value, let us say V1, and then actually you are multiplying with an elemental distance dt. So V into dt is the height multiplied by this elemental distance. That is, if you take one strip, so that strip width area, so the strip area actually is getting calculated with V into dt. Now, like that, actually, we are calculating the area. Now, if I divide this entire with capital T, which is the entire T value, if you calculate it, if you divide with the entire T value, V into dt, that means V into dt products actually we have added for the entire thing, and we have calculated, or we have divided with the entire T value. Then obviously, actually, it will give the average value of V, right? Got it or not? Right? This is exactly what we are doing. So this is what is the average value calculation. So this is the standard mathematical methodology to find out the average value. So here actually we wanted to calculate for the basic waveform, we will use this formula. Whatever may be the kind of waveform you give it, the method of calculation of the average is this one only. So this is a standard methodology. So in general, the average value is, so 1 by T integral V into dt. So this is the average value, right? Now, this average value, we call this as the DC equivalent of AC. So, the DC equivalent of AC. Right? So, that means V average of AC, which is of 5 volts, is as equivalent as that of 5 volts of DC. Right? Because AC is continuously changing waveform. So here one value is different, here the 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 value is different. But in case of DC, it is a fixed value. So this is the fixed value. But here actually, as it is continuously varying, then if I ask the fundamental question, what is the equivalent DC value? This is exactly is the equivalent DC value. But it may not be the same amount of the heat that it is going to produce. That is a different concept. So here, the same amount of DC quantity is equivalent to the average of this particular value. And this is the formula we use to calculate the average value, right? Now, based on this understanding, suppose you tell me what is the average of the sinusoidal waveform. What is the average value of the sinusoidal waveform? Guess how much is the average of this waveform? You can do this value, right? So that is V average is equal to 1 by T integral 0 to T and Vm sin omega t dt, d of omega t, right? So this is the way actually we calculate it. So this is 1 by T integral 0 to T Vm sin theta d theta. Right? And this value actually we usually count as the theta, right? So theta is equal to omega t, which is what we call as the angular velocity. And I said, so I committed that actually I will be explaining what is this angular velocity. And before that, actually, just actually assume that this theta equal to omega t, and then actually we will calculate it. And this, so if you calculate as t, so we are interested in this length. So whatever may be the quantity you are going to use it. If it is t, then we will divide with t. If it is the angle, we will divide with the angle. That's exactly is the basic principle, right? So this is 2 pi is the period here. And height, so here actually we divide with 2 pi and Vm sin theta d theta. So integral, this is also until 2 pi. So what is the average value? Calculate this and tell me. 1 by 2 pi in integral 0 to 2 pi Vm sin theta d theta. What is this value? So did you calculate and set that answer 2 Vm by pi? Did you calculate it? No, it is 0. Right? So why? Because this is a positive area and this is a negative area, and positive area A1 and negative area is minus A1, which is exactly equal. Right? Positive waveform, negative waveform are equal. Integral actually won't take care of area. I hope you know that fact. So in +2 standard, you might have learned that if you do the integration and suppose actually if there is positive, so above the x-axis and below the x-axis, the areas are there, it will add up algebraically. So this is treated as a positive area and this is treated as a negative area, and essentially it will come out to be 0, right? Yeah, so essentially it will come out to be 0. So for AC, if you take the complete waveform, it will always be 0 because the positive area and negative area are one and the same. Because of that reason, for AC, we always talk about the half wave. So if you take half wave, then it will be the positive value. Then actually you will come up with some number which is the average here. Got it? So that is the reason when we calculate the average area, we have to calculate 1 by pi. So Vm by pi integral 0 to pi sin theta d theta. So this is how actually we have to calculate it. So this is Vm by pi and integral sin theta. So derivative of cos theta is minus sin theta, integral sin theta is minus cos theta, and upper limit is pi and lower limit is 0. So this is minus Vm by pi and cos pi minus cos 0 and cos pi is minus 1. So this is minus Vm by pi, right? And then actually, so this is cos pi is minus 1 and cos 0 is 1 and minus of minus will be plus. So this is 2 Vm by pi. So if you take only until this particular point, then the average is coming out to be 2 Vm by pi. And this is exactly what we see in the case of the full wave rectifier. So the full wave rectifier actually, it will convert the waveform like this. So this is the full wave rectifier, right? So this is being the full wave rectifier until pi actually we take the average value and this average value will come out to be 2 Vm by pi. Got it? Right? Ideally, if you take it as it is, it will be 0 always. So we say 2 Vm by pi is the full wave rectifier. And in case of half wave rectifier, actually, we will be calculating the half wave rectifier. So this is, and this is half, and again this is half. So like this, actually, it will be continued. Now in this case, the period is this one. So period is 2 pi, but the area is exactly the same thing what we have calculated even the previous one. So this is 1 by 2 pi is the area, integral 0 to pi, Vm sin theta d theta plus integral pi to 2 pi 0 d theta. So this is the way actually we calculated for the entire range of the period. So this is, so just give me a minute. Right? Okay. So 1 by 2 pi is common. So this is 0. Hence actually 1 by 2 pi and Vm into minus cos theta. Upper limit is pi, lower limit is 0. So this is plus 2 Vm by 2 pi. So these two will cancel. So this is Vm by pi. This is actually in the case of the half wave rectifier. So only the period got doubled, but essentially the area is same. In this case, actually, the period is only till this point because the same waveform is getting repeated again and again. Got it? The same waveform. So the period here it is pi itself. And in case of half wave rectifier, period is 2 pi, but area is counted for only 1. Now this understanding is very important, not only from the electronics perspective, even from the power electronics as well. And also you need to understand that we never talk about the average value in case of AC directly dealing with power systems. So in the power systems and the machines, all such kind of subjects, actually, we never talk about the average value at all. We always talk about the RMS value. Why? Because the average value concept is essential only for the electronics people. So because you will be dealing with the DC. So the rectifier is going to be used to supply some kind of circuit, right? The rectifier. Now there what you are interested is all the transistors, MOSFETs, everything is actually just designed only to work for DC. So you wanted to identify what is the equivalent DC value that is coming out at the terminals over there. That is the reason the average value is intentionally meant only for the DC calculations, not for AC calculations. We don't talk about the average value at all. Just it is not required. Got it? But we always talk about the RMS value. So I hope you understood the concept of the average value. So I hope, is it understood? Got it? Right? And then actually suppose if I give you any other waveform, suppose if I take the triangular waveform like this, So this is a triangular waveform and V equal to T is the waveform, and let us say this is the time period T, right? And this is the period and the same time period here, and like this actually this is the same time period T. Then you calculate the average value of this. What is the average value of this? The curve is V equal to T and the period is capital T. Now what is the average value of this curve? Is it T by 2? Okay, maybe true. Let me check it. So this is 1 by T is the time period and integral 0 to capital T, which is the entire period, and this curve is V is equal to T. So V dt, and this is the average value. And V average is equal to 1 by T integral 0 to capital T, T dt, and this is 1 by T and this is T square by 2. Upper limit is capital T, lower limit is 0. So this is T square minus 0 divided by capital T into 2. So this is T by 2. Yes, you are right. Right. So this is how actually we calculate the average value. Now, if I give one more waveform, let us say this is, right, and let us take this kind of waveform, and this is actually repetitive in nature. So this is like this actually this waveform continues. Now let us say this is, so let us say this is 2V and this is minus V, right? 2V and minus V, and the period is, so this is of T by 3 and this is 2T by 3, right? Or this entirely, so this is the capital T. Now you calculate the average value for this one. What is the average value of this? Is it 1 by 3? Okay, let me tell you, but T should be there, right? Is it T by 3 you mean? Okay, so by looking at this actually I will just explain. See, this 2V and this is T by 2. So 2VT by 3 is the area here, and this area is 2T by 3, 2T by 3 and minus V, right? And 2TV by 3. So 2TV by 3 minus 2TV by 3, which is equal to 0. Got it or not? Which is equal to 0. And hence actually the average value, if you calculate it, it will come out to be 0. Now let me explain. So we will see that integration itself. So integral V average is equal to 1 by T, and until T by 3, 0 to T by 3, the value is 2V dt, plus, and from T by 3 to, so total capital T. So this is minus V dt, right? And this value if you calculate it, so 1 by T and 2V into T, and upper limit is T by 3, lower limit is 0, minus V into small t, upper limit is T, lower limit is, so T by 3, right? And this value is 1 by T, so 2V into 2V T by 3 minus, so T minus T by 3, 2T by 3, so 2V T by 3. So this value is 0. Got it? So the average value is 0 for this particular scenario. I hope you got it. You can directly check it. Whatever the area you count here, the same area it will come in here. Okay. But I hope you understood, right? Upper area and lower area actually it is getting compensated. So that's the reason actually we will not find out the average value here for this kind of waveform, right? And this kind of waveforms actually we will see in our analysis of power electronics, right? So there are actually any kind of shape you take it, as long as there is a shape, the average value calculated is of, this is 1 by the time period integral 0 to T and whatever may be the value, so V of T dt. So this is the way we calculate the average value. Got it? And this formula is fixed. And it is up to you how do you want it to take the waveform. So whatever may be the complex waveform, whether it is divided into multiple parts, whether it is a single waveform, so everything actually it will automatically take it. This is a single formula to calculate the average value. I hope you understood. Any questions you can ask me. Any questions? Right? And then actually, so average value is the DC equivalent AC waveform. So if you notice, this average value we calculate only in the context of the rectifiers, because when we wanted to generate from AC source and we are more interested in DC. So the DC value we want, suppose if you want 5 volts of DC, then how do you calculate 5 volts of DC? That is the average value we will calculate, and we say that this is 5 volts of DC. Got it? So that is why actually we need this average value. And the RMS value. What is this RMS value is? By definition, this is the root mean square value. Right? Root mean square. So this is a different term, this is a different term, this is a different term. Suppose actually if I have, let us say I1, I2 are actually 1, 2, 5, 7. 4 values are there. Now if I ask you to calculate the RMS value of this, that means what we do is, first actually root mean square. So we need to square it. 1 square plus 2 square plus 5 square plus 7 square. Right? And we are calculating the mean of it. Right? So squared it and we took the mean of it and then we calculate the root of it. So this is the value of the RMS. Got it? So this is how actually whatever may be the number of values you take it, and individually each and every value is getting calculated by square, and we will divide with the average, and then actually we will calculate the root of it, which is what we call as the root mean square. Now let us understand the context of this root mean square, why we are so much concerned about the root mean square. Suppose actually you take this particular scenario. Suppose I have a DC source like this, then there is a resistance here, and let us say this is V. And the amount of the current that is flowing is actually V by R, and this is the value of the current. Now, if I ask you to calculate what is the heat or actually what is the power loss in this resistance, what you do, we calculate the power loss is I square R. So this is the I square R value. So if I square R value calculated, so that is actually the heat produced. In the resistor. Right? Now actually I take one more scenario. The same resistance I take, the same R value, but rather than this DC source, I keep a AC source. So I keep an AC source, and this is actually a sinusoidal waveform. Actually, I will be giving it. So this is a sinusoidal waveform that was given. Now, what is the value of the current? So this is V by R, but V is Vm sin theta. Vm sin theta is the value of the current. Now, depending upon the theta value, where theta is omega t. So this is V is equal to Vm sin omega t. Now, depending upon the t value, the theta value continuously it changes, and according to the theta value, it can have this value or this value or this value or this value. It can have any value at any point of time, right? Now, what is the current if I ask? It's not a fixed value. Like in the case of DC, we have taken a fixed waveform. So this is, if it is DC, then actually what is the value of the current? You always talk about this value, which is value of R, V by R. But here it is not like that. The current value, if you wanted to ask, then actually this is how actually the current is changing. Now, if you ask what is the current value, then immediately I will ask at what time you want. So because it is time dependent. At different times, the current value is different because it is a sinusoidal waveform which is continuously varying with respect to time. Now, if I ask you to calculate what is the heat produced in this resistance, how do you calculate? How do you calculate the heat produced in that resistance? If I give the sinusoidal waveform, if it is DC, straight away you calculate I square R value. But here it is AC, then how do you calculate? Tell me, how do you calculate? I ask you to calculate what is the heat produced. V average square R. Now you tell me whether that is correct or not. Can't we do this? No. So V average square by R actually will not give the correct result, because V average you have taken, suppose actually you take this expanded value. Suppose this is I1 value. So this is I0, this is I1, this is I2, and this is I3, this is I4, and this is I5. So total 5 values we have taken. So I1, I2, I3, I4. And then actually you have taken the average of this value. So divided by the entire time period, let us say whatever the time period you take it. And this is the V average, I average actually you have calculated. Right, I average value, this is how actually we calculate. Depending upon the voltage value, it is accordingly changing it. Now actually you wanted to square it. So that means actually this entirely we will be squaring it. And you are multiplying with R. Now, do you say that actually I1 plus I2 plus I3 plus I4 plus I5 whole square is equivalent to I1 square plus I2 square plus I3 square plus I4 square plus I5 square? Can I equate these two values straight away? Mathematically, is it correct or not? Right? Mathematically, it's not correct. But what exactly is physically happening? That also we can see. Now, see this. In this particular waveform, at one instant actually there is no current, zero. That means at that time actually there is no heat produced. At another instant of time, so I1 is the current actually which is passing through. So hence actually I1 square R at this instant of time. And similarly, at this instant of time, I2 square R. Instantaneously, the values keep on changing. So I3 square R and I4 square R, I5 square R. So these are all the values of the currents that were produced at I1, I2, I3, I4, I5 values, or actually at T1, T2, T3, T4, T5 values actually. This is the amount of the heats that are going to be produced. Now you can take the average of all the heats. Got it or not? Right? You can take the average of all the heats. Then actually that will be the more or less accurate value you were able to achieve it if you are able to take the average of all these heats that were produced at different times. Correct or not? Understood? Right, that's exactly what we do. So that is what we take is I1 square R plus I2 square R plus I3 square R plus I4 square R plus I5 square R whole divided by the 5 values. Right, 5 values we have taken, and this value is, if you take R common, then this is R, I'll write it on the right side. So I1 square plus I2 square plus I3 square plus I4 square plus I5 square whole divided by 5 multiplied by R. So this I can equate to I square R, which is the equivalent current, which can produce the same amount of the heat. So this I value square root of I1 square plus I2 square plus I3 square plus I4 square plus I5 square divided by 5, and this is the value which we call this as the IRMS, because this can be equated to I square R. Got it or not? So this is the fundamental understanding from where we got this RMS value. So this is the basic definition. So it is the same amount of the heat that could be produced with the DC. Suppose actually this RMS value, whatever we take it, the same amount of DC value, if the current passes through it, then it will produce the same amount of the heat. Got it? So the heat is different. The actual value of the voltage is different. Though we calculate I average value and VRMS value and all, in DC what we are interested is V average value in DC, because that is the amount of the voltage, that is what we are going to supply to over there. But in AC we are more interested in the RMS value of the current rather than the voltage. So this is essential because it will produce the same amount of the heat that DC can produce. Got it? Understood? So this is exactly what we do it. So as there are 5 values, we can take it. Suppose if it is a sinusoidal waveform or any function of t, so this is V of t. Now what we do? So individually each and every value we take it. So VRMS, if you wanted to calculate it, and let us say this is Vm sin omega t or Vm sin theta. If you take it, Vm sin theta is the value of the voltage. Then so this is, you need to take the average. So this is of 2 pi. You need to take the average because the period is of 2 pi. and we need to individually square each and every value. So that is Vm sin theta whole square. So this value is an instantaneous value. Instantaneous value meaning at that instant what is the value. So that is the instantaneous value. So the instantaneous values are squared it, and we have taken the average of it, and for the overall actually we take the square root of it. Got it? And this is the way we calculate the RMS value. Got it? I hope you understood this concept. So if it is a current, then it is the current waveform. If it is a voltage, then this is the voltage waveform, we take it. But essentially, this is exactly what we do, and integral 0 to 2 pi, we take it. Clear? Understood? Yes or no? Right? Now here, as we are taking the square of the waveform, positive and negative actually it will not make any difference for us. Suppose if you square this value, so this is how actually you are going to get it. And if you square this value also, this is how you are going to get it. Because the negative value square actually is the positive value. So this is the square value. So V square value is this particular graph. So this is how actually the square waveform actually it will come on the top. The square waveform, right, is always a positive value. Now if you wanted to take the average of it, you don't need to consider 2 pi. You can even consider until pi only. Because this is repeated afterwards. Got it or not? So if you calculate this, I will give you two values. See this VRMS, I will calculate as 1 by 2 pi integral 0 to 2 pi Vm sin theta whole square d theta and square root of it. So this is actually I have considered entire 2 pi range. So this range. Another way to calculate is VRMS is 1 by pi because I take only half, and integral 0 to pi Vm sin theta whole square d theta under root. You calculate both of these values and tell me what are the values you are getting it. See, here also 2 pi and here also 2 pi, here also pi and here also pi. And that was decided based on the waveform, because the square waveform actually anyway it is the same value, positive and negative. Hence actually the period for the square waveform is pi, the period for the normal waveform is 2 pi. Got it? Can you calculate and tell me what is the value? Fine. Okay. So in both of these cases actually you should get the same answer. So I will solve this one, and here 1 by pi times of and Vm square and sine square theta integral 0 to pi. So VRMS square we will calculate, and then at the end we will take the square root of it, and Vm square is a constant which we can take it out, and 1 by pi and sine square theta d theta, right? Sine square theta d theta, and this is Vm square by pi into sine square theta. So sine square theta can be written as, we know that actually, so 1 minus 2 sine square theta equal to cos 2 theta. So 1 minus cos 2 theta by 2 is the sine square theta value. So this value you can just replace it, integral 0 to pi 1 by 2 minus cos 2 theta by 2 d theta. So this is Vm square by pi into, so theta by 2 minus, so derivative of cos theta, so derivative of sine theta is cos theta. So integral cos theta is sine theta. So this is sine 2 theta by 2 into 2. Upper limit is pi, lower limit is 0. Now upper limit and lower limit, this portion actually will be 0. So sine 2 pi is 0, sine 0 is also 0. And whatever is left over here, it is Vm square by pi times of pi minus 0 divided by 2. Right? So this is finally, it was coming out to be Vm square by 2. So VRMS is equal to Vm square by 2 or it implies Vrms equal to Vm by root 2. Got it? So this is Vm by root 2 is the average value for AC source. Vm by root 2, exactly, right? And if you take even for this one also, it will come out to be Vm by root 2 only. There is no difference. Vm by root 2, right? Now, suppose if I give you a triangular waveform, you tell me what is the RMS value for the same triangular wave what we have calculated the average value. Now this one actually V is equal to T, then you calculate, this is the period. Tell me what is the RMS value for this. Because this was asked actually once in UPSC, RMS value, average value calculations. So we need to understand these fundamentals. So because actually the methodology is same, irrespective of whatever maybe the waveform you are going to take it. Most of the times we tempted that actually RMS value is always the Vm by root 2. But we forgot to think that actually the value is dependent on the shape of the waveform. So the shape of the waveform, if it's sinusoidal, then it is Vm by root 2. But if it is a triangular, it's not. Got it? So the RMS value and average value are dependent on RMS and average value are dependent on RMS and dependent on the shape of the waveform. Got it? Shape, it depends on the shape of the waveform. Clear? Any questions? Right. So can you calculate the RMS value for this shape? Right? V by root 3 you say. So you are saying that actually V by root 3. What is the value of V? Because V is a function of T, right? Which value you are talking about? What is the value of V? Because V is equal to T I have given, which is a variable function. So Vm, exactly. So this is the Vm value. So this height is going to be of Vm. Now in that case, let us calculate. So let me tell you. So this is Vrms square we take first. And the period is 1 by T. And integral 0 to T. And V square is T square and dt. Right? T square dt. So this is 1 by T. T cube by 3. Upper limit is T. Lower limit is 0. And this is 1 by T into T cube minus 0 divided by 3. So this is T square by 3. So this is Vrms square value. So Vrms is equal to T square by 3 under root equal to, yeah. So this is T by 3, right? And this value. Now here actually this T also needs to be converted, because if you notice V is equal to T, so T is equal to the maximum value that is possible here. So this is Vm by root 3. So this is the way actually we have to calculate the RMS value. Now, suppose if the areas are equal, do you think that actually, see this, suppose if I give this particular waveform. Now the same kind of waveform what we have calculated earlier. So this is of 2V and this is of minus V. And this is of, until this point it is T by 3. And from here to here, this is of 2T by 3. The same waveform, whatever we have calculated earlier, for this actually, you calculate the RMS value for this. So here actually, earlier these areas are same, but now actually, does it matter? So will it come out to be 0 RMS value? Average is anyway 0 for this. You calculate the RMS value and tell me. V root 2. Okay, so Vrms actually you say that this is V root 2, right? Yeah. So let me calculate. See this. So the square waveform actually, if you wanted to draw the square waveform, 2V whole square is 4V square. So this is 4V square until this point. And then actually minus V whole square is plus V square only. So this is V square height. Sorry, V square. And then actually this length. So this is 2T by 3 and this is T by 3. Now you take the average of this. So this is 4V square into t by 3 v square into 2t by 3 whole divided by t. So this is v RMS square. So this is t will cancel, and then actually 4v square by 3 plus 2v square by 3. So this is 6v square by 3, and this is 2v square, and v RMS is equal to root 2v. Exactly, right? What you said is correct. If you do the integration also, it will come out to be the same. So I have straight away taken the area and added it, because the square of 2v is 4v square, which is this height, and the square of minus v whole square is plus v square, which is of this height, and this length is 2t by 3, this length is t by 3, and this area, so this height multiplied by this width, and this height multiplied by this width. So if you do that, so t by 3 into 4v square and v square into 2t by 3, and we have taken the average of this. So root mean square value we have calculated it by square rooting this entire thing. Actually, we will square root it. So that is coming out to be root 2v. Got it? So I hope you understood a fair idea, right? So how to calculate the RMS value and what is the importance of it. So RMS value is, it is the equivalent amount of heat that it is going to generate from AC source, because AC is instantaneously changing. Every minor second, actually millisecond, it will change continuously. But DC is not like that. So if a fixed amount of the current, if it is going, how much heat it can generate, the same amount of heat should be generated by continuously changing waveform. That is the importance of it. Got it? Clear? Any questions you can ask me. Any questions? Yes, the RMS value is just to calculate the power. There is no other purpose for that. Just to calculate the power. Right? And also one more important factor actually we need to understand. And this is actually many people will get confused. When we calculate the power in a resistance, so let us say this is DC. Then actually the amount of the current that is flowing is I, and I value we calculate as V by R. And this is the resistance here. And then actually, so the power is equal to, right? Power is equal to voltage into current. Right? So actually, if you notice, we know that W is, so the potential is defined as the work done per unit charge. Right? The work done per unit charge. And this is what is the potential. So this is W equal to W by Q is equal to the potential V, right? And this is by definition. So the work concept, as I said earlier, work is nothing but if there is a particle that it can move, then actually the displacement multiplied by the force applied to move that particle is called as the work. Now here actually there is an electric charge. So maybe positive charge, maybe negative charge that is going to be present. And that charge actually, it will always tries to attract another positive articles, or actually it will repel if it is the same charge. Now in doing that, it will try to move the particle. Suppose if there are two protons that are there, one proton will try to move the other proton. So there is a force that is going to be exerted on that. Now for 1 coulomb of charge, how much actually it can repel? Or for 1 coulomb of positive charge, how much it can attract the negative charge? So that is actually, it is moving the particle from one location to another location. That's exactly what we call as the work. So work done per unit charge is defined as the potential for us in moving that. Now here actually, the battery also, if you take it, the electrons and the ions are separated, and then actually it will try to move it. So in moving, actually, we say that if there is some kind of work it was done, and for how much charge, how much is the work actually it is going to do it, and that's what we call as the potential. So from now onwards, actually, we always treat as potential is the standard quantity. We don't consider about the charge magnitude. We don't consider about the work it can do. Got it? So V is equal to W by Q, or W is equal to, so W is equal to V into Q. Got it? So W is equal to V into Q. Now here, when we wanted to calculate the power, so power is actually dW by dt. So rate of transfer of work. right? Rate of transfer of work, and this is for a constant voltage V into dq by dt, so V into I. So this is the power actually we are going to calculate it. Got it? So this is actually from the physics definition we got this value. So V is equal to, so V into I is the value of the power actually it is going to generate it. Now in case of DC it is straightforward and easy to understand. There is no doubt because this is a constant amount of the voltage that is going to be present here and a constant amount of the current it is going to drive, and the product at every point if you calculate it. So if you try to draw the graph of V into I, which is the product of these two, a constant value getting multiplied with a constant value, it will give you a constant result power. So this is the power curve. So power is a constant value in case of DC, but in case of AC, how it will be? It is continuously changing waveform. So just now actually we discussed the average value and RMS value because it is a continuously changing waveform. Now actually if I ask you to calculate what is the power, it is going to be drawn by a sinusoidal waveform, and here the same circuit actually it was given, but it is connected to an alternating voltage source, and this is a sinusoidal waveform. Now this is R and this is V is equal to Vm sin theta. Now you tell me how much is the power drawn by this? How do you calculate? Because this is very crucial concept. This is the only concept actually which will make the difference from electronics engineering to electrical engineering. So electrical engineering, we always talk about the AC sinusoidal waveform, and always actually the inductor, capacitor, everything comes into picture. In that, power calculation is the key point, and power calculation is the one actually which will make the entire power system. Got it? Now you tell me how do you calculate this simple resistance connected with Vm sin theta. This is a big subject, very big subject. Entire power system is dependent on this. You tell me how do you calculate? You might have used it, right? In your graduation, actually, you might have calculated the power. Now, in case of DC, you can straight away calculate because this is a constant value. But in case of AC, what do you do? See, okay. So I will give this as an assignment. You think over it. What can be done to calculate the power, and what is the best methodology you can adopt to calculate the power? This is very big concept. And then actually you try to calculate, suppose if rather than the resistance, if I connect the inductor for the voltage source, the same V is equal to Vm sin theta, it was connected. Wherever theta required, we simply calculate as omega t. And suppose what if I connect this to the capacitor, how much power it is going to consume? Calculate the value of P, which is the product of V into I. And for the resistance, how it is going to be calculated. Suppose if it is an RL circuit, then how do you calculate the power? For a sinusoidal waveform, this is R, this is L. If you are able to do this on your own, you can master the power systems. Yeah, you need to calculate the power across these resistance and inductor and the capacitor separately. And the voltage waveform that was given is Vm sin theta. Then what is the power dissipated in this? What is the power dissipated in this? What is the power dissipated in this? And what is the power dissipated in this? Got it? So fundamentally, you think in the lines, that is DC, everything is constant. Voltage is constant and current is also constant. Because voltage, current are constant values, the product of V into I at any point of time actually it is always a constant value. But here it is not. In AC actually it's not. If you take average value, what we did, because it is not constant, depending upon the purpose, we came to a conclusion. So we want the DC equivalent voltage value. For that, what we have taken? Every value we have taken and averaged it. So that is a different methodology, so that actually you can conclude something. Because at every minor second actually we cannot count it, right? Because infinite variations actually you can see within 1 second. Now all the variations you cannot track continuously. For that actually we have given an equivalent value, which is what we call as the average value. And the second thing is, the second requirement is the RMS value. You wanted to calculate how much is the equivalent heat it can produce. The AC equivalent value for the DC is the RMS value what we have calculated. Now exactly the power actually we have calculated in the normal way in case of DC. For AC, what we can do, because AC actually continuously it is changing. Voltage also changing and current also changing. Then actually you have to calculate the product, and the product will be continuously changing, right? Obviously, right? Got it or not? Product also continuously changing. Then you have to come up with a conclusion. What variation? So in the first case, we have taken the average value. In the second case, we have taken the RMS value. Now in the third case, for the power calculation, we always, whenever in AC, if we talk about the power, that is the average power. It is by default understood, but nobody actually knows this fact. By default, it is understood that that is the average power. Got it or not? Because it is continuously changing. Now, what do you calculate? So Vm sin theta is the voltage waveform. Correspondingly, calculate the current value depending upon the resistance value, and then actually you take the product of it everywhere, and then actually you just calculate the average of the product. Then that will be the average power we are going to calculate. Same value you calculate for the inductor, same value you calculate for the capacitor, same value you calculate for RL. And whatever I have explained on this board, if you are able to properly understand and derive your own derivations for each and everything, you can master power systems and power electronics. Got it? This is as simple as this. Such a big subject just depends on this. Got it? Okay. So this you take it as an assignment and try to solve it. That's all. Thank you.